So, last week we have talked about that design of FIR filter mainly using two methods. One is called windowing methods, one is called frequency sampling methods. So, in the last week I have discussed about what is how to design an FIR filter using windowing methods and using frequency sampling methods. So, this week let us start with that design of FIR filter using approximation methods. So, what is the name? Name is called design of optimum equiripple linear phase FIR filter using optimization methods. What is the meaning? Meaning is that I have a given and desired frequency response. This is my desired frequency response, which is omega p. Okay. So, that is I want to design an ideal low pass filter. Now, then I have designed an filter. Let us say I have designed an Hn, I have designed an Hn and I calculate H of omega. So, I get the design H omega. Now, what I want to know that how close is my desired frequency the design frequency response to the desired frequency response. So, the error between that two things are the error. So, if I say this one minus this one is the error of my design. So, I have to optimize the error to get that as close as to the desired frequency response. So, that is the main motto of these methods. So, what I said, design of an optimum equiripple linear phase FIR filter using optimization methods. So, why we go for these methods? Let us talk about that. The window methods and frequency sampling methods are relatively simple technique, as you say that simple technique to design linear phase FIR filter, but there is a certain limitation. What are those limitations? Now, if you see that if I use windowing methods, I know the transition bandwidth delta it depends on what type of window I use. So, if I use rectangular window, then the transition bandwidth is 4 pi by I think 4 pi by m, but transition bandwidth is less. But what is there that in case of rectangular window, the problem is pass band, stop band ripple. Stop band ripple is very high. Now, if I want to reduce the ripple, then I have to go for the other window. Once I use the Hamming window, I know the transition bandwidth is increases from 8 pi by m. So, the for same order, my transition bandwidth is larger. So, what is the problem in windowing methods? The lack of precise control over the critical frequency omega p pass band edge frequency, omega s the stop band edge frequency. So, the transition bandwidth delta is nothing but stop band edge frequency minus pass band edge frequency. So, this part I have a lack of control that depends on window, which if I want to reduce the ripple, the transition bandwidth is increases. If I want to increase the ripple, transition bandwidth is decreases. That is okay, but there is a lack of control in windowing method. Similarly, frequency sampling method also, that I know that I have sampled that frequency, whether the type 1 or type 2, in both the cases I have designed using frequency sampling methods, but desired frequency response may not be as control, as there is no control over this transition bandwidth. So, that is the main drawback in design on FIR filter using window methods and frequency sampling methods. Now, I want a methods which has a desired control on transition bandwidth. So, what I want to design an FIR filter using a methods which can give me a control over the transition bandwidth and the ripple in the pass band and stop band. So, that is why I said I want to design an FIR filter which is equiripple FIR filter linear phase FIR filter I want to design using optimization methods. So, optimization is nothing but a graph of, let us say that suppose I want this filter. Now, I design this filter. Now, I know this is my design part and this is my desired part. I know the error. Now I said I want to minimize the error so that my design response is as close as to the desired response that I want. So that is nothing but a approximation. So that approximation is done using Chebyshev approximation problem. That is used in mathematics. You know the Chebyshev approximation problem in mathematics, you have studied it, that to optimize that distribution approximation. So I have a desired distribution, I have a given distribution, then I change the parameter so that it close to the desired one. So that approximation is called Chebyshev approximation problem. The same method is used to design this kind of filter. How do you use it? We design and we introduce an weighted approximation error between the desired frequency response and actual frequency response. So I derived an weighted approximation error function, weighted approximation error between the, so what I want that okay, there may be a error between the desired one and the desired frequency and the actual frequency response, but that error should be eventually spread across the pass band and stop band. So when I say there is an error and that error is eventually distributed over pass band and stop band, so I can say the pass band and stop band both the way there is a ripple is there. So I may want this kind of frequency response, but I can lead down to this kind of frequency response. So there will be an error that ripple in both the pass band and stop band. So I use an weighted approximation error function which will be allow that which kind of error I desired. So instead of depending on the window and depending on the methods of frequency sampling, I can say this is an approximation problem and I define an error function which error is eventually evenly distributed among the pass band and stop band, and that error is I have a control, I want to minimize that error. So that is the acceptable design. So how do I do that? That methods. So let's say again you have already known that. So this is the given frequency response of a low pass filter. So you know this is called pass band ripple, this is called stop band ripple, this is pass band edge frequency, stop band edge frequency, and this difference is called transition bandwidth. So all those things I have already known, and that is same for all kinds of filter design. So this is desired frequency response, the frequency response provided as per the specification. So ideal low pass filter is this one, but ideal one we cannot design. So people said that okay, I require a low pass filter whose stop band attenuation is 60 dB, pass band is this dB and transition bandwidth is this one. So that I know. So now said, since the ripple is distributed evenly among the pass band and stop band, so I can say that in pass band I require this frequency response. The magnitude of the frequency response is this one of the filter. Delta 1 is the deviation in the pass band. So I can say this one is less delta p is equal to delta 1, and instead of delta s I said peak to peak delta 2. So here also delta 1 is peak to peak, and here also delta is 2 is also have a peak to peak. So it is minus delta 2 plus delta. So the stop band ripple will vary from ideal one is 1. So 1 plus delta and 1 minus delta 1. So that is the stop band ripple variation. Pass band ripple variation, instead of delta s, I said pass band has a ripple, then I said in middle there is a line. So there is an delta 2 plus and delta 2 minus. So delta 2 plus and delta 2 minus, that is the ripple condition. Instead of 0 to delta s, I said minus delta 2 to minus delta 2 to plus delta 2. So, that is the deviation in stop band and that is the deviation in pass band. Okay. So, that I have known. Now, I know that there is 4 methods for design of linear phase FIR filter. So, in case of case 1, which is symmetric unit response and order n is odd. So, order of the filter n is odd and the impulse response is symmetric. So, that is the requirement for the linear phase. So, this is my linear phase requirement plus minus. So, I know this is requirement. So, if it is symmetric, then I know h of n is equal to h of n minus capital N minus 1 minus small n. That is my symmetric requirement. And now capital N is odd. That means order of the filter is odd. Okay. Now, I know if the order is odd, already we have derived the for linear phase condition, what is the frequency response, that we have already known that. That is my physical. So, HR is the design. If h of n is my impulse response, then this is will be my HR for my design frequency response. So, HR is nothing but a frequency response of the design filter. So, if Hn is my impulse response which is symmetric and the order of n is odd, then this will be my frequency response. Now, in this equation, if I make k equal to this one, so this part is equal to k, then I can say that I can define alpha k which is equal to h of n minus 1 by 2 for k equal to 0 and for k equal to 1 to n minus 1 divided by 2, it is 2 h n minus 1 by 2 minus n. Then I can say the HR omega is nothing but a k. So, k equal to 0 to n minus, so I can this is k equal to 1, sorry, this will be k equal to 1 to this one, because this is one term is already extra. So, I can say k equal to 0 to n minus 1 by 2 is nothing but a generalized form. So, I can say n minus 1 by 2 minus n is equal to k. So, instead of summation size n, I write summation size k. Okay. So, k equal to 0 to n minus 1 by 2 alpha k cos omega k. So, alpha k are the filter coefficient or ak, let us say it is ak, not alpha a. So, ak is the filter coefficient. So, I can say the frequency response is nothing but a convolution between the filter coefficient and cos omega k. Cos omega k is nothing but a for k equal to 1, 2, 0, 1, 2, 3, 4. So, for every k I get an omega. Understand or not? So, it is nothing but a convolution between the filter coefficient alpha k and cos omega k. Cos omega k is nothing but define the different frequency. So, this is for symmetric condition and if n is odd. Now, let us say the same thing when the n is even. We have already derived this one in my, I think in my first the 8th week first lecture, you can see linear phase requirement, it may be a second lecture. So, this is my frequency response if h of n is my impulse response. Again I said k equal to this one, n by 2 minus n. Then I can say bk is equal to this one, let us say bk is equal to this one I define, then I can derive, I can rewrite this hr omega is nothing but a cos omega by 2 b cap cos omega k. So, this is my first one, this is my second one, and these two difference between the two equation is nothing but a relationship between the bk and b cap k. So, this is a b cap k. Okay. So, that relations will come like this. If I 1 and 2 equalized and do the relationship, this relationship you can derive. So, now you can see that HR omega is written in a one kind of format. One is bk into cos omega k. So, in case of first one, it is 1 into this one. In case of this one, This is convolution, where this is the coefficient which is related to the Hn. Bk is related to the Hn, because if you see the Bk I define in term of Hn, so there is a linear relationship between the Bk and Hn. So, Bk is related to Hn, Ak is related to Hn. So, all Hn basically define the filter coefficient. Here also Bk define the filter coefficient and cos omega k. Only one constant term is there, which is cos omega by 2 instead of 1. In case of symmetric even, it is cos omega by 2. Similarly, for antisymmetric, again you take this one and again k equal to this one, again approximation, you can get same kind of equation. This part is same. Ck is related to C cap k is related to Hn, linearly related to Hn. Again it has a multiplication factor sin omega. Okay. Now again if I say that n is even in case of antisymmetric, again I can get the same things, only multiplication factor is sin omega by 2 and rest are same. So, if I write all the four equation, this equation, this equation, this equation and this equation in a summarized format, I can say HR omega is nothing but a, I can say it is a q omega multiplied by p omega, where q omega in this case q omega is equal to sin omega by 2. In this case q omega is equal to sin omega. In this case q omega is equal to cos omega by 2, and in here it is nothing but a q omega is equal to 1. So, if I want to write down these four equations in generalized form, which is HR omega is equal to q omega and multiplied by p omega. So, q omega in case of type 1 or case 1 it is 1, in case of case 2 it is omega by 2, in case of case 3 it is sin omega, in case of case 4 it is nothing but a sin omega by 2. What is p omega? P omega type 1 k equal to 0 to this one, type 2 this one, type 3 this one, type 4 this one. Now, if you see q omega does not depends on Hn, because nothing component of Hn is here. It is nothing but a 1 is a constant, cos omega by 2 it is nothing but a function of omega, sin omega is nothing but a function of omega, sin omega by 2 it is nothing but a function of omega. But here all are Ak, Bk, Ck all are related to H of n. So, I can control HR omega by controlling p omega. By how can I control p omega? By controlling of p omega depends on Ak, Bk, Ck or Dk, and all are related to Hn. So, if I find out the filter coefficient precisely, and if I want to find out the filter coefficient precisely such that I can design a perfect HR omega which is as close as to desired frequency response. So, how do you do that? So, the problem is, so if you see the p omega in a common form I can write down. Let us say all are Bk cos omega k, Ck cos omega k, sorry there is a cos omega k, Dk cos omega k I can write down. So, all are same kinds of things. So, I can say Pw is nothing but a k equal to 0 to L. Let us say here L is only vary, L is equal to n minus 1 divided by 2 in case of odd and n by 2 minus 1 in case of n is even. So, I can say only L will vary, L will be n minus 1 by 2 if n odd, L will be n by 2 minus 1 if n is even. Otherwise, this is same, otherwise all are same. Alpha k is a variable which is alpha k, which may be a k, which may be a big K, which may be C k, which may be d k. So, this alpha k represent the parameter of the filter which are linearly related to the impulse response of the filter. So, if I say HR omega, so HR omega is nothing but a combination of Q omega and P omega. I have only control on P omega, Q omega is a constant. So, how do I control P omega? By controlling H of n, which depends on alpha k. So, alpha k is called the filter parameter. So, let us the real value desired frequency response is H dr omega. That means, I want this frequency response. So, I will take a slide here. Let us say I want a frequency response which is my desired frequency response, which is H dr omega, which is this one. Now, I design HR omega, which is maybe this one. Then I want to compute the error between the desired one and design one. Let us say I define a function W omega which relatively size the error in the different frequency band. So, I can say I want to monitor the error by using W omega. So, let us say I said okay, instead of this kind of error is sufficient for me. So, I design a function which is W omega. So, W omega is the allowable error. I can say W omega H dr omega is my new one. This I want, and I design W omega into HR omega. So, that is nothing but a E omega, my error. So, error is nothing but this one. So, this W omega is used to quantize the error. So, I can say error is nothing but a W omega common H dr omega minus HR omega. Now, what is HR omega? So, I can say W omega H dr omega minus P omega and Q omega. HR omega is nothing but a Q omega and 2 P omega. So, if I take Q omega outside, so W omega into Q omega is equal to H dr omega, H dr omega divided by Q omega minus P omega. Now, if I say this one is nothing but a W dashed omega and this one is nothing but a H dr dash omega. So, what I said? I said H dr dash omega is nothing but a W omega and Q omega. This is here, and H dr nothing but a H dr omega divided by Q omega. So, I can say error is nothing but, so this will be replaced by W dash omega and this will be replaced by H dr dash omega. So, I can say error is W cap omega H dr cap omega minus P omega. What is P omega? P omega already we have said this one is the P omega, where alpha k is the control. So, I can say this is my equation of error. Now, if I told you I want to minimize the error with respect to what? So, if you see here, only I can minimize the error with respect to AK or alpha. I can say alpha k, not cap, alpha k with respect to alpha k. So, this is alpha k. So, alpha k is the filter parameter with respect to which I want to minimize the E omega. So, is a minimization problem. So, take the derivative. So, I want to find out a set of alpha k that minimize the maximum absolute value of E omega. Minimize the E omega with respect to alpha omega. Alpha k is nothing but a taking derivative with d E omega divided by d alpha k. So, with respect to alpha k, if I take the derivative and if I minimize this one, so what I want to determine the desired alpha k which is related to impulse response of the filter, design filter, so that EW becomes minimum. So, what is EW? Is the difference between the desired response minus design response. So, that is the approximation problem, or I can say optimization problem. I want to optimize the error. So, that optimization done using Chebyshev approximation problem. So, that is a method by which I do this optimization. So, if you have a mathematical background, you can do that optimization and you can do that. I am not covering it purposefully, because if I cover it for a BTech engineer, it will be very huge, because it can take another 1 week course for this whole optimization problem description. So, what is our job? Our job has to, alpha k has been determined, construct the original frequency response and hence Hn. So, once I minimize the EW, so for that set of alpha k for which the error is minima, so that from that alpha k value, if I say that Hn, I can design Hn. So, alpha Hn is given, alpha k is derived, calculate the error, minimize the error and modify that Hn. So, once I do an approximation problem, then I get the desired, once I go close to the desired frequency response, I can say that set of Hn is my optimal set of impulse response which is close to the desired frequency response. So, that is the optimization problem. So, what is the solution of this optimization problem? So, solution is obtained by via alteration theorem. There is another theorem called alteration theorem or alternation theorem. This alternation theorem is used to solve this. Now, there is one method, Park and McClellan used Riemann's algorithm to develop the procedure for design. So, what is the procedure? I have to design a set of Hn, derived alpha k, find out the error, then I want to minimize this error changing this Hn. Once I said this is optimum, EW is optimum, that set of alpha k for that set of Hn is my desired impulse response of the filter. So, that approximation is done using an algorithm which is Riemann's algorithm. You can see that book, or you can go to the any standard DSP book, you can get it. If you are interested, then after covering the course, then you can raise a question, so send a mail, then I can take another class for this one, so that optimization problem you know. Okay. So, that is the design methods for FIR filter using optimization methods. So, if I summarize the FIR filter, you have to know FIR filter, finite impulse response filter, the property, it may be a linear, symmetric or antisymmetric, the order of the filter may be even and odd. So, for the linear phase requirement, we know what kind of frequency response will be there. So, that is common for all kinds of design. Then I go for the design of 3 methods. One is called window methods. I can design FIR filter using window methods. So, using algebra, I can calculate h of n, multiply by the Wn and then convolve with the input signal, I get the desired output. Similarly, I can go for the frequency sampling methods. There is a type 1 sampling, type 2 sampling, and those equations are there. I can design that FIR filter for a given specification using that method also. Then I go for the optimization methods, which is computer based design methods, which can be optimization algorithm can be run on a computer to find out a desired set of HN for which the difference between the desired frequency response and the design frequency response is minimum. So, that is the summary of FIR filter. So, from the next lecture I will go for the IIR filter design. Okay? Thank you.